Good morning, Year 4. So the last lesson we ended off at the three types of radiation, alpha, beta, and gamma radiation. Today we're going to talk a bit more about the type of decays that will release these three types of radiation. So the first one will be the alpha decay. Now turn to page 250 of your textbook. You will be able to see at the top box, it says alpha particle. Please highlight that. Highlight helium nucleus. So remember we said that the alpha particle consists of 2 protons, 2 neutrons, and this is basically the helium nucleus. So let's try this out. If uranium-238 that containing 92 protons decays to thorium-234 plus an alpha particle, how would the equation look like? Try this out now. So remember we said that 238 is the mass number, so that is the number that's going on top. So uranium will be U. And then since there are 92 protons would be the proton number that's at the bottom. Now when it decays, it becomes thorium. Thorium would be TH, symbol for thorium is TH. And then they tell you 234, so therefore the mass number on top is 234. Now, plus an alpha particle. Alpha we say is 4, 2, right? So just check that the top numbers must add up. And then since the bottom number for alpha is 2, I'll take 92 minus 2 to get me the 90 for thorium. So just a reminder, mass number and atomic numbers must balance on each side of the equation. Okay, and the alpha particle can be notated as 42 helium or 42 alpha. Alright, try example 7 on your own. So we have plutonium-239 decaying by alpha emission to uranium, atomic number 92. So let's start with, did you get this? Now because they tell this is the mass number, so mass number will be written on top here. They tell you that, now we don't know what this is, right? But you know that you have uranium and the atomic number is 92. Now atomic number, remember we said that this is the same as the proton number. So you write it down 92 here. Now since it produces a alpha emission, alpha decay, so you have your 42 alpha. So you just need to take 239 minus 4, you get 235. And then how do I get 94? I take 92 plus 2 to get 94. Okay, let's move on to the beta decay. Now, beta particles consist of high-speed electrons. So they're emitted by isotopes that have too many neutrons. One of these neutrons decays into a proton and an electron. The proton remains in the nucleus, but the electron is emitted as a beta particle. Now this is on 251 of your textbook. You can see right at the top. Okay, try this out. Carbon, the symbol is C. Nitrogen, symbol is N. Carbon has got atomic number 6. Okay. So try this out now. Did you get this? So since I told you that this is a carbon 14, so I write down carbon and then 14 at the top. And then nitrogen 14, so 14 is also at the top. Now beta, we said that beta is an electron, right? So electron means that there are no neutrons, okay, and then there is only the charge it'll be -1 at the bottom, because if it's a proton it'll be +1. So since the electron it'll be -1. So look at this, 7 plus -1 gives us 6. Okay, so the beta particle being negatively charged has an effective atomic number of -1. There you go, atomic number. Okay, and then it can be notated as E0 -1 or beta, 0 -1 beta. Alright, so either one is acceptable. Now try this out on your own. Do you get this? Quite simple, right? So sodium again, mass number 25, so that's right on top here. Atomic number 11, so that's at the bottom here. They tell you it decays by beta emission to magnesium. So I write down magnesium here. Then beta, so I write down my 0 minus 1 beta. And then the top values should add up to give me right hand side should be equal to left hand side. So since this is 0, this must be 25. And then what plus minus 1, or rather what minus 1 gives me 11. So 12 minus 1 gives me 11. Okay, let's move on to gamma decay. Now, gamma decay is the emission of electromagnetic radiation from an unstable nucleus. Gamma radiation often occurs after a nucleus has emitted an alpha or beta particle. But sometimes it need not emit alpha or beta particle, it can just emit gamma radiation. Alright, so one example would be cobalt-60. Now cobalt-60, after it undergoes, it decays with, it undergoes gamma decay, you still get cobalt-60 with some gamma radiation. Now gamma radiation is energy, right? So what happens to your resulting cobalt particle? Initially it has excess energy, decays to cobalt-60 with less energy plus gamma radiation. Okay, so both alpha and beta decay causes an isotope to change atomic number and therefore changes its element. The alpha decay also causes a change in mass number. So what are the changes for the atomic number and mass number for each of these decays? Alpha, remember, is a 4, 2 alpha. Beta is 0 minus 1 beta, right? So remember the top one, this is our atomic number. Bottom would be our mass, sorry, wrong. The top number is our mass number. The bottom would be our atomic number. So what will happen when to an element when it undergoes alpha decay? The atomic number will reduce by 2, right? Because they're here. Reduced by 2. Mass number will reduce by 4. What about for beta? Atomic number will increase by 1. Mass number remains unchanged. Gamma would be 0, 0. So no change for both atomic and mass number of the particle. Alright, try this out on your own now. Okay, so since beta remember at the bottom is minus 1. So over here, this would be 59 and this would be 27. So that 27 minus 1 gives me 26 on the left hand side. Part B, over here is 224. So my minus 4, I get 220. Alpha would be 4, 2. So right hand side, I add them up equals to left hand side. This will be 88. Part C, 0 minus 1, this must be my beta particle. So let's do the values first, okay? So 0 plus 16, up here will be 16. 8 minus 1 gives me 7. Now, what's 16? 8, that's actually our oxygen. Okay, now, challenge yourself. Try this out. Write equations showing how lead-2O2 can decay into gold. Pause here and try it out first. So this is one of the possible reactions. Lead will undergo alpha decay to give us mercury. Mercury then undergoes another alpha decay to give us platinum. And then platinum undergoes a beta decay to give us gold. Now there are other correct solutions, and so if we had given any other solutions and still obtaining gold, that's fine. Let's move off to half-life. Turn to page 252 of your textbook. So what's half-life? Now when a nucleus decay into a different atom, the time taken for half of the sample to decay is called the half-life. So on 252 of your textbook, can you please highlight the first orange box? The half-life of a radioactive isotope is the time taken for half the nuclei present in any given sample to decay. Now, can you go further down under activity and half-life? Highlight the words in bold. The SI unit for activity is becquerel, BQ, capital B, small letter q. Highlight that, please. So 100 becquerel means that 100 nuclei are disintegrating per second. So that's the SI unit for activity. Now, some medical applications for half-life. They make use of different types of nuclide, and they put it into the body to be able to tell what's happening. Okay, these are some of the half-lives of some radioactive isotopes. Don't have to memorize them, it's just for your interest. Okay, let's go to example 11. Now, example 11 tells us that strontium-90 has a half-life of 29 years. In 2012, a sample contains 19.2 grams of strontium-19. The mass of strontium-90 in the sample halves every 29 years. Okay, so what's happening? Can you tell me when will the mass have fallen to 0.15 grams? So when will the mass have fallen to 0.15 grams? I want to know, how long does it take for the sample to reach 0.15 grams? So what do? Now you can draw a table out like this. And then you can say that, okay, year 2012, there is 19.2 grams. Now, they tell you that the sample halves every 29 years. So over here, we're plus 29 years. And after 29 years, what happens to the sample? It decreases by half, right? So initially you start off with 19.2, decreases by half, you get 9.6. Another 29 years, you get 4.8. Another 29 years, you get 2.4. Another 29 years, you get 1.2. Another 29 years, you get 0.6. Then what else must we do? Another 29 years, you get 0.30. And then another 29 years, you get 0.15. So add 29, how many years will that be? In what year? So it'll be 2215. In year 2215, we will have 0.15 grams of strontium. Okay, now next. They want us to calculate the mass of the isotope remaining at 11 a.m. Now there are different ways of doing it. You can either use this equation here, or you can use the method I just taught you just now. Try it out here. So at 10 a.m. in the morning, a radioactive sample contains 80 grams of isotope. 80 grams of a radioactive isotope. If the isotope has a half-life of 20 minutes, calculate the mass of the isotope remaining at 11 a.m. So 20 minutes, this is one half-life, another 20 minutes, second half-life, another 20 minutes, third half-life. And this makes up 1 hour, right? So from 10 a.m. to 11 a.m., it has gone 3 half-lives. So what do? First half-life becomes 40, second half-life becomes 20, third half-life 10 grams. So you can draw the table out and do that. Alright, so this is at 10 a.m. This is 80 grams. At 10:20, 40 grams. At 10:40, 20 grams. At 11 a.m., 10 grams. Alternatively, if you use the formula that I've shown, final mass equals to half to the power of n times initial mass, and n represents the number of half-life. So basically from 10 a.m. to 11 a.m. and each half-life is 20 minutes means that there are 3 half-lives, right? So 3 half-lives, mass of isotope, if you take half to the power of 3 times the initial mass, which is 80, you get 10 grams. Okay, so this is the half-life formula. where A is the new mass present, A naught is the initial amount or initial mass. Now this amount can mean like the number of particles, number of nuclei, all right, and then n would be the number of half-lives. So just take note that how many half-lives do we have? It'll be total time divided by 1 half-life. Now, and make sure that your units are the same. Sometimes they give you time in terms of like 10 a.m., 11 a.m., 12 a.m. But then the half-life they give you in terms of minutes or seconds. You need to make sure that you convert it such that they have the same units. Alright, try this out on your own now. So they tell us that the mass decreases from 24 grams to 6 grams over a period of 60 days. They ask us to calculate the half-life. So what do? How many half-lives will there be? 24 to 6. So 24, after it undergoes one half-life, it will be 12 grams. After it undergoes a second half-life, it will be 6 grams. So how many half-lives will there be? 2 half-lives. So 60 days, how you get the half-life? Divide by 2. You get 30 days. Now try this out on your own. So they tell us that Source Z decays with half-life of 3 hours. At 9 a.m., the source has got activity of 16,000 becquerels. The activity halves every 3 hours. Yep, that's right, half-life 3 hours, right? So when would it have fallen to 125 becquerel? What time will that be? So you can write this down from 6 a.m. Why 6 a.m.? Sorry, that's the answer. Okay, so what you do, you draw your table out. Okay, so 9 a.m., what do you have? 16. You have 16000 becquerel. That's activity. Then every 3 hours, right? So the next 3 hours later, it drops by half, so 8,000. 3 hours later, it drops by half, 4,000. Another 3 hours later, 2,000. Another 3 hours later, 1,000. Another 3 hours later, 500. Another 3 hours later, so this time will be 3 a.m., right? It'll be 250. Sorry. And then another 3 hours later, so that'll be 6 a.m., it'll drop to 125. So what time will it be? 6 a.m. Okay, again, pause here and try this out. So isotope X decays to isotope Y with a half-life of 2 hours. Now, before I go through the answer for this, those of you who have bothered to watch this video, send me an email to tell me what is one food item that you look forward to when COVID-19 ends. Send me a private email, and those of you who do that will get 2 extra marks for the next graded assignment. Okay, let's go to example 15. So isotope X decays to isotope Y with a half-life of 2 hours. So let's highlight that. At 2 p.m., there are 6,400 nuclei of X. When will the nuclei of X fall to 25? So again, you can draw it out. Now, do I really care about nuclei Y? Not really. So at 2 p.m., there's 6400 isotope of nuclei of X. 2 hours later, it'll be 3200. Another 2 hours later, 1600. Another 2 hours later, 800. Another 2 hours later, 400. Another 2 hours later, 200. Another 2 hours later, so let's write that down. So it becomes 2 a.m., right? 100. At 4 a.m., 50. At 6 a.m., 25. So when will the number of nuclei X fall to 25? At 6 a.m. Now, if we want to talk about in terms of number of nuclei of Y, then initially it'll be 0, right? Then remember, these two must always add up to what the total number of nuclei is, which will be 6400. So when it drops to 1600, there'll be 4800 nuclei of Y. So basically, number of X and number of Y must always add up to 6400. Alright? Okay, try example 6 on your own now. So let's go through the answer. They tell us that half-life of 3 hours at 8 a.m. is activity of 600 becquerel. What would the activity of 2 p.m. at 2 p.m. be? So those of you who like to draw it out, you may draw it out. I like to draw it out actually, although it actually you waste quite a bit of time. So at 8 a.m., 600 becquerel. They tell us half-life is 3 hours, right? So 8, 9, 10, 11. At 11 a.m., it will be 300 becquerel. 11, 12, 1, 2. 2 p.m., it will be 150 becquerel. Again, pause here and try this out. So they tell us that substance P decays to substance Q with a half-life of 15 minutes. At 9 a.m., there is 1280 nuclei of P. Complete the table. And how many nuclei of substance P will there be left at 11 a.m.? So 1280 of P. At the start, we won't have anything of Q. Okay, 15 minutes later, so one half-life later will be 640. Over here will also be 640 because when you add them together, you get 1280. Then this will be 320. How much Q will we have? 1280 minus 320. 320, you get 960. Then another 15 minutes later, let me just 320 divided by 2, 160. Then 15 minutes later, it drops to 80. And then Q will be 12. So add this together, you get 1280, right? And then 40 and 1240. So at 11 a.m., continue doing it. At 10:30, what do you get? This is 20. This would be 1260. At 10:45, you have 10, and this would be 1270. At 11 a.m., this will be 5, and this will be 1275. So, how many nuclei of P will we have at 11 a.m.? 5. Alright, pause here and try this out. So a sample contains 8 billion nuclei of hydrogen 3 atoms. Hydrogen 3 has a half-life of 12 years. How many nuclei should remain after a period of 48 years? I want nuclei remaining. Okay, so how many half-lives are we talking about? 48 divided by 12, you get 12, 24, 36, 48, 4 half-lives, right? So 4 half-lives, you just take, so what you do, you can use the formula, half to the power of 4 times 8 billion, and then you end up getting 500 billion. Now, what if I want to find half-life from a graph? So, if you look at this example here, there are many ways of finding half-lives. One would be through calculation, the other one would be from a graph. So if initially I started with 500, one half-life later, it will have 250 number of nuclei left, right? So I can always draw dotted lines here, come down, get the time taken. Alright, but so this is the time for one half-life in terms of seconds, so about 30 seconds. But if you want it to be more accurate, then you can repeat this method for other initial nuclei numbers and then taking an average. So for example, I can take from 200, I start from 200. So at 200, it will have 40. After one half-life, it will be 100, right? So this will be about 70. So I'll just take this timing here, which is 70 minus 40. That gives me 30. So you notice that one half-life is really about 30. So I can take this plus this divided by 2. So 30 plus 30 divided by 2, that still gives me 30. Okay, Now, estimate the half-life of the substance whose decay graph is shown opposite. Pause here and try this out. So if I had taken 68, if I started with 600 becquerel, one half-life later, it will have 300. So this is the time taken for one half-life, which is about 20 seconds. Okay. Pause here and try this out on your own. Now, they ask you to draw a graph, so please use graph paper. If you had drawn it, you would notice that it's about 2 hours. Now, even if I don't draw, okay, I just look at this. If I started with 650, one half-life later will be 325, right? So 325 is somewhere over here. So then you know that, okay, your timing should be somewhere in between 2 to 3 hours. So if you draw it out, you will be able to get a better idea of what the half-life is. Alright, some effects of ionizing radiation on living things. So like your gamma radiation. It can damage or kill living cells. It can lead to genetic mutation or cancerous growth. It can cause radiation burns. Okay, so beta and gamma radiation can cause radiation burns. There is this thing called radiation sickness, which is why when people deal with radioactive substances, they are advised not to stay in the venue for too long. So if you're doing lab work, you will have to get out of the lab for, you have to take breaks so that you're not exposed to radiation for such a long period of time. If some people do like something related underground, where there's radiation underground, they cannot stay there for too long. Just like when, say, the nuclear reactors exploded, right? And there were a lot of like say in Fukushima, there were lots of Japanese who went to help to clear the remains, or when they were just cleaning things up. They couldn't stay in there for too long, otherwise you'll get radiation sickness. And sometimes when you're exposed to too much radiation, it can ultimately lead to death. Now please highlight this on page 248 of your textbook. So what are some safety precautions? 249 of our textbook, let's highlight there. What do you need to do? This is in the blue box on the top right hand corner. So you can see the 4 bullet points there, highlighted, stored in a lead container. Alright, then you make sure you pick it up with tongs and not by hand. You should handle it for minimum time possible, okay? So as short a time possible. And any waste should be kept in steel containers buried in concrete bunkers. So you should not be leaving them out. And we're done for this chapter. So please complete worksheet 25.1.